Okay, now let's start this second part of our lecture. So, we will be talking about image representation, image sensing and acquisition, how images are formed, and then sampling, quantization, and resolution. Okay, so first, few words about electromagnetic spectrum. In your intermediate level physics, maybe you might have learned something about electromagnetic radiation, that this is set of waves contains some energy, it travels through space, and it has both electric as well as magnetic characteristics, and there is a large set of these different wavelengths and different frequencies, and the wavelength range from kilometer to nanometers. Okay, and then the electromagnetic spectrum, so the range of all these possible frequencies with this large number of waves with different characteristics. Okay, for example, here we have this large range. Okay, and if you look here, like wavelength, so wavelength with very small number, and here wavelength even a kilometer. Okay, so and on this side, when you go to this large wavelength side, so you are going towards radio waves, and then when you come in this direction, so you are passing waves like X-rays, and then the wavelength with somehow larger the waves with somehow larger wavelengths are ultraviolet. Okay, and in this small region, these are the waves are the waves which our eyes can perceive. So this is called the visible spectrum, and the range is like for violet light we have this range, and for blue light we have these different wavelengths are for the visible light. So in this range, at this position, we can perceive the light, but we cannot see X-rays, or we cannot see radio waves, or we cannot see microwaves. Okay, so this range, this range is the range which our eyes can perceive, but the range larger than this or smaller than this range cannot be perceived by our eyes. And there is another point, like the light cannot pass through objects, but when you look at X-rays, so it can pass through the object, and the reason is that it has more energy. Now at the energy side, at the top row, when you look here, so when you go to the left side, the wavelength has more energy, on right side the wavelength has less energy. So the waves with larger are energies with this ratio, it can penetrate through different objects. The criteria for penetration is that it should have more energy, and the the wavelength should also be shorter. If the wavelength is shorter, then it can penetrate through the objects. Okay. If you want to see molecules, then you will have to use waves with wavelength which is too short. If there is a wave with larger wavelength, then the smaller object will be just skipped. But if the wavelength is very small, then it can like hit the smaller objects, and then you can project the image on some plane. But if the wavelength is larger than the image size, not exactly like larger, there should be some relation, but if the object is smaller, then you have to use some waves with smaller wavelengths. Otherwise you cannot image those smaller objects. Okay, and now image representation. Usually in the normal coordinate system, we have like we start 0 0 from this position, but in image coordinate the 0 0 are started at top left corner, top left. Okay, in the normal coordinate you start from the okay, so in the normal coordinate your 0 0 is this bottom left, but in image coordinate you have, this is like the not the standard representation. Different tools can represent images differently, but this is the representation which most of the application adopts. So sometime there can be some tool which take this 0 0 from bottom right or from bottom left. Okay, there are some tools, but usually majority of the tools, these represent the 0 0 from top left. Okay, we can have color images, we can have gray level images. In our course mostly we will be dealing with gray level images, because the techniques which we will follow for gray level images can be applied on color images, with the exception that in color image in gray level image we have one channel, but in color images we have 3 channels. So the algorithm which we will use for gray level image can be applied to color images, with the only change that you have to apply that algorithm on 3 different images. Okay, so color images are actually a combination of more than one image, where each image maintain the different levels for different color channels. Okay, for example, in gray level we have 0 to 255 gray levels. So if we have color image, there will be one image for red channel, and then there will be 0 to 255 levels for red, 0 to 255 for green, and so on. And then it's not necessary that always this range will be 0 to 255. It depends, which we will talk later. Okay. And then usually the images are represented, the 2D images are represented as a matrix, because usually for matrix this is because of the mathematics which we will be using. There are a lot of formulas for matrix operation, and when we adopt these matrix terminologies, then we can make our job easy by taking these algorithms from the matrix algebra. Okay, so we can also represent image as a 2D matrix, and then different operation on images can be done by taking different operation from the matrices. Okay, we already talked in our last lecture about the image acquisition, how images are formed. We said that there is continuous scene, and then we use some imaging system which project this continuous scene on a plane with the change that we have to convert the continuous nature to discrete nature. But in this lecture we will go in some more details. Okay, so in the imaging system we will be having some sensors. Okay, these sensors will be sensitive to some different types of light, and then these sensors will be activated when the light falls on these sensors. Each sensor creates some voltage, and then this amount of voltage is transferred to the image plane. Okay, when light falls on the sensor, then the sensor is activated and it creates some voltage level, and then that voltage level are considered as intensity levels. Okay, now we can have either one dimensional sensor or two dimensional sensor. I think you might not remember, but 15 or 20 years ago there were cameras which were having this one dimensional sensor, and it was taking around about 3 or 4 minutes to acquire an image, because the method which was used in these one dimensional sensors were that it was going through the scene one line at a time in one direction. Now in modern cameras we have sensors, two dimensional sensors, so the whole scene can be captured at the same time, and then like it reduces this acquisition time. Okay, now how these images are discretized and how this voltage level is converted to the intensity level. Let's say that we have this image. Okay, and we are projecting only this area. Okay, this one line. Okay, so what will happen, it will start from this position here. The intensity levels are too high, like from this position to this position, and then this high intensities are represented here. Then from this position onward the intensities decrease. Do you understand when I say increase or decrease? I use the term high for white pixels and low intensity for black pixels. Okay, so when I say that the intensities are high, then it means that these are white pixels. Although you can use these terms like other way around, you can use low intensity for white and higher intensities for black, so it depends. Okay, now here I have these high intensities, then abruptly the intensities decreases, and at this moment I have very low intensity, and then from this position onward the intensities are then increasing. Okay, here the intensities are increasing, and at this position it reaches the peak. So like at this position the pixels are whiter as compared to its neighboring pixels, and then from this position onward the intensities are decreasing, and when the sensor reach at this position, so again the intensities are increasing. Okay, now this area represent these positions. Okay, and if there is this one-dimensional sensor, then you can go through the other part of the image. Okay, okay, now I have this continuous, I acquired this continuous range, almost continuous. It wouldn't be continuous, but it would be close to continuous. It depends on the amount or number of sensors in my sensor plane. Do you understand what I mean? Okay, now when I say that, okay, I have this region and I shift the intensity from this region to some storage plane, and then I can either take this position or this position or this position. So it depends on the number of sensors, how much sensors I have. If I have like sensors scattered through the whole sensor plane, then the continuity will be close to the real. Okay, so let's say that I have acquired pixel values which are too close to each other. Okay, and now my next point will be whether I maintain this high resolution or I just downsample these high voltages. Okay. Okay, so now in this next image I have skipped some values. Okay, now here I kept this, but I skipped pixels in this region, then I skipped pixels in this region, and then I skipped pixel. So this is sampling. I am skipping pixel at this region, here, here, here. So I consider some pixels, but I discard rest of the pixel to reduce this number of pixels, and this is sampling. So it depends like how much samples I want to take. And usually you set these values in your cameras when you take images. So you set whether you need high resolution image or you need low resolution image, you need an image for sending this through emails or for your laptops or whatever, and then the resolution is adjusted according to your requirements. Clear? Okay. Now the next point is quantization. So one is sampling and one is quantization. Okay. So we will, next slides we will talk about quantization. We have this image, we have captured the voltage through the whole continuous scene, and then here we are considering some samples. Okay, we don't consider the whole continuous acquired intensities, but we consider some intensities. And let's say that the voltage or intensity range are, and this is some like not exact but somehow close in scale to this curve. Okay, now the question will be whether I want to store these intensity levels in this format, or I want to reduce this range. Here the range is like from 0 to 50. So I can also think about taking this or rescaling it from 0 to 25, okay, or from 0 to 16. Do you follow me? What I mean? If I want to take a black and white image, then what would be the values? 0 and 1. Okay. And then what I will do, like this is 0, so it will be 0, and this is 50, so it will be, if this is like, this will be 1. And what I will do with the 20? Why? Huh? Okay, so I will just like divide the range from 0 to 25 will be considered as 0, and from 25 to 50 will be considered as 1. So this is quantization. What? Scaling, yes. But then there is another benefit, like this is not as straightforward. If you are taking black and white image, then this means that for each pixel you would need 1 bit of information. Okay? It will be like in 1 bit you can either store 0 or 1. So if you want to take black and white image, you need 2 values, and then you can have 1 pixel, 1 bit of information for each pixel. Clear? But if you need more details of your image, because now the problem is that when you take black and white image, then the curve will be different. Your curve will be here I am. Okay, now the curve will be like this. Your curve will be like this, and then what will be the problem? You will be having less details in your image. Okay, if you want to take more values, more than 2, up to 4, if you want to take like 4 values, 0, 1, 2, 3, then you need 2 bits per pixel. And if you want to take 8 values, then you need 3 bits per pixel. Clear? Okay. We already talked about this, that a digital image is not the exact copy of the scene, it is actually approximation of the real scene. Now, can anyone explain why it is approximation and why it is not the real object? Because of this downsampling and quantization. So I will give this question in exam, that like what is quantization and what is sampling. Okay, but it will not be what is. It will be like some images, and then something like the connection between this quantization and images. There will be 2 images, and then the question may be like, what level of downsampling has these 2 images, or what level of quantization these 2 images is. Okay, I think you should already know that how the values for this image would look like. How many values should I need for this? This is not a black and white image. If you look this, there are 3 levels. Yeah. So if you have 3 values, so this image can be represented in a best way. If you take more pixels, more bits per pixel, then I don't think it will give any benefit. Clear? Because we have 3 levels, and for 3 levels we can have like 2 bits per pixel. Okay, if you take more bits per pixel, it wouldn't give any additional benefit. This is just an internal representation that, like, for the boundaries you have zeros, and for the inside you have value 5 and then 1, but you have 3 values. Okay. I think we will talk about this in our medical imaging course, that how X-ray images are formed and how these are acquired. Okay, so we will skip this slide. Okay, now the next point is spatial resolution. You already know about like the good quality image and bad quality image. If an image has low number of pixels, then we say that it's low quality. If there are more pixels, then we say that it has good quality. Okay. Here you have different images, and in the top left the quality is good, mean the spatial resolution is good, but in the bottom right the spatial resolution is low and the quality is bad. This is like common sense. I will come to this slide later. Okay. Quality of 2 images with same contents and same size. I have 2 images, the contents are same and the pixel size is also same. So what do you think about the quality? Would this be, these 2 images will be having the same quality? Okay. What the rest thing? I have these 2 images. It's a 5 by 5 matrix for each. Oh, okay, sorry. These colors, these are not the contents. This is just a 5 by 5 matrix, 2-dimensional array. There has nothing to do with these colors. Sorry for taking colors in this array, 2-dimensional array. There are 2 images. The number of pixels in both the images is same, and the scene is also same, and the lighting condition is also same. So do you think that these images will be same? But why? It will be same. You mean same? Okay. How many of you think that these 2 images will be exactly the same? Can you raise your hands? Okay. And there are few who have some reservations, like Ehsan and okay. So just raise your hands who thinks that it's not necessary that these 2 images will be same. Afruddin, do you think that these will not be same? And the rest? Okay, so only one person thinks that it's not necessary that these 2 will be the same object, images. Okay. Sorry. Okay. Now I have some values in these matrices. Okay. This is 25 pixels in the left image and 25 pixels in the right image. Now these are numbers, so we don't know whether these 2 images are same or different. Clear? These are numbers, so we cannot say anything. It looks same, like these are just numbers. Okay? Sorry. Now these 2 images These have the same number of pixels, but on the, do you think that these two has the same quality? Huh? No. The image size is same and the scene was same, like there was some person and this is an image of someone. Okay, and these two images, the scene is same and the resolution is same.
Environment
Surrounding is also same. Everything is same. But now look at these images, how these are identical.
Sir, one color is extra in left.
What?
One color is extra, sir, and is compared to the right one, gray one.
Okay. Okay, now this is like now our discussion is going in another direction. For many of you, these two images are same actually.
What's the background?
Yeah, the background is not a problem. But the foreground, okay.
The left side has more details as compared to the right one.
Yeah, but do you think that the left image, it has good quality as compared to the right one, or no? Like for those who says that left image has good quality, this is good quality image.
Both are the same.
So actually, we are confusing about the qualities or the structure of these.
Yeah. Okay, so for what I started this discussion now, I didn't get that objective. Okay, let's think about this. Do you think that the top left and the bottom right, these two images are same?
No, structure is same.
Structure is same, but in the top left, I can see the nose of this person. Clear?
Yes.
But in the bottom right, I don't see the nose. Okay? Now, in the top left, I can see the lips. But in the bottom right, I cannot see the lips. Okay? So, you have to accept that the top left and the bottom right, these are not same. The top left and the bottom right, these are different images. Do you agree?
Yes.
Not in the sense that the images, but the quality of the top left is different than the bottom right. Okay? But the pixel size for these two images is same. Okay? Resolution for these two images. Now forget about the images in the middle, but just focus on these two images. Okay, this one and this one. Both has same number of pixels. One is a good image and the second is a bad one. Number of pixels are same. Now, what's the explanation for this? If the number of pixels and the resolution is same,
The value of the pixel.
yes,
Yes.
gray levels. Okay, gray level for these two images are different. In one image, we have only 2 levels. In the other image, we have 256 different levels. Okay, and this is actually the difference between a color image and a black and white image. In black and white image, we have a few number of levels, but in color image, we have a large number of levels. Okay, So the point was that the image quality is not only depend on the number of pixels, but also on the quantization or the gray levels, because in one image I have reduced the quantization to 2 values, but when you increase the number of gray levels or yes, so you will get better quality images. When you reduce these levels, you will get bad quality images. And then, like, what's the relation between the number of gray levels and number of bits needed for a pixel? So the number of gray levels is directly related to the number of bits for one pixel. If you have a black and white image, then you need 1 bit per pixel for representing the image. But when you have 256 gray levels, then for each pixel you need 8 pixels, 8 bits per pixel. Okay, and that was my point actually. Okay. So, did you understand? Yes. Okay. Okay, now there is another problem that is called saturation. And saturation is that you have.
Sir, I have a question.
Uh-huh.
Sir, if we use cameras and they have the same resolution, for example, we buy cameras in the market
Yeah.
and they have the same resolution.
Uh-huh.
The maximum resolution supported it. So,
Okay.
can we say that which one of the camera will be a better one? Because the quality depends upon not only on the number of pixels, but also on the value per pixel.
So the one for which a pixel has more bits, okay? If everything is same, but in one camera you have 20 bits per pixel and another you have 40 bits per pixel.
So we don't see such like things on a camera. They just write some things.
Usually in the market, this resolution is considered as sufficient criteria. But I think these cameras, they already consider the maximum number of bits representation for a pixel. Although I'm not sure like for all cameras, but I think that these cameras already consider the maximum number of bits. So I don't think that in market we need these further details.
Usually they are megapixels.
Yeah. So even in megapixels, if you have low number of bits per pixel, then still you can get bad quality. So this megapixel value doesn't guarantee that in any case. Yeah.
Color information is also there. And like this 24-bit.
I think if you look at the manual, not the camera, but if you look at the manual, so I think you can get these information. On the camera, you can just look at the number of pixels, but the detailed information, or you can go to the website of these manufacturers, and then you can get these information. Okay. Okay, now in this image, do you see some problem? Some pixels are very bright and some are very dark. Okay. So now if you rescale these whole values, then maybe like decreasing the values of the brighter pixels and increasing the values of the darker pixels. But it's not very easy. Like you can spread these values uniformly. If you have this image, and so it can be a good exercise to decrease the brighter pixels and increase the intensities of darker pixels. Okay. Okay, resolution, how much is enough? Now, usually in practical application, theoretically we think that like we should, in any case, we should take good quality images, means super resolved images having more number of pixels should be acquired. But in practical use, we will always face problems when we send images through internet, through emails. Then we cannot send good quality images with high resolution. Okay, so in that case we need images with low size. Low size means low number of pixels. Similarly, for storage purposes, if in any case you take images with very good quality, then you will face this storage problem. You will need a lot of space to store these images. So the question would be, what value of resolution is sufficient? Okay, so this depends on the application. For what purpose you acquire images. Okay. Now, apparently, like the left one is a good image, the right one seems a bad one. Okay, but if you have some software which just count the number of cars, then for this purpose the best image would be the image with very low number of pixels, because it will reduce the computation time. So for that purpose you should select the right one. Okay, but if you want to read the number plate, then you cannot do this from the right one. Then in this case you need high resolution image. So it depends on your application, and in any case you have to manage your resources and computation time. Okay, so you have to look your application and then you have to go for images. If your application cannot work with low resolution images, then you have to go for high resolution images. Okay.
So when we resize an image, we decrease the number of pixels.
Yes. Or there can be two types of resizing. You can maintain, but in that case you wouldn't like you skip some number of pixels in the middle and assign values from the neighboring pixels. So that wouldn't reduce the size, but that would reduce the number of stored information. So when you want to store the image, it will take less space, but when you want to display the image, you will get full size image with somehow bad quality. Okay. Okay, so there are three different images. In one image we have low details, in second image we have medium details, and in third image we have high details. So like low detail, low resolution, medium detail, medium resolution, and high resolution. Okay. Okay, so here we would stop and then we will continue next week. Okay.